A small startup airline has decided to provide service to 5 Midwest cities. That's 10 direct routes. Let's see if we can't make it a little easier on them by using spanning trees. Now, we have been talking about this idea of a tree. And remember, a tree is a connected graph, one that has a path from every single node or vertice to every other node. Now, whenever it comes to a tree, we have one less edge than we do nodes. And that makes it so that with a connected graph, there's exactly one path between any two nodes in this graph. We also talked about neighborhoods. So a neighborhood is the set of all vertices connected to a specific vertex directly with a single edge. And so for the neighborhood of A, that's just B. B is the only one that A is connected to. But the neighborhood of B, a little bit larger. It's connected to A, D, and E. All right. Now, this is going to be important when we start applying algorithms to our graph, which may have cycles, in order to reduce it down to an optimal tree. And what is that optimal tree? Well, let's talk about this definition of something called a spanning tree. So let's define this thing called a spanning tree. Starting out with a graph. If I have a graph, and this is just any graph, it's not necessarily a tree, and we've got a number of edges connecting these vertices together, all right? Now, this is not a tree. We know it's not a tree because, well, it is connected, and that is one of the requirements of a tree, but we have a cycle here. The tree has to have one fewer edge than it has vertices. I have 1, 2, 3, 4, 5, 6 edges. I have 6 vertices. This is not a tree. The spanning tree says we take a graph and we delete one of the edges. We remove one of the edges until it becomes a tree that still connects all of those nodes, all of those vertices. Now notice, I did delete the one between F and E, but I could have just as easily deleted the connection between B and E, or I could have deleted the connection between A and B. So there are a number of spanning trees that could have resulted from this particular graph. Now let's start out with a very simple graph. I have 3 nodes or vertices, A, B, C. We're going to make it a complete graph. And remember, a complete graph is where every single node is connected to every other node. Now, whenever it comes to a complete graph, coming up with a spanning tree, we're going to have to remove a number of these edges, at least 1 or 2 of these edges, because we've got a cycle here. So there, for this 3-node graph, so we have A, B, C, we could have A and C connected and A and B connected. We could also have A and C connected and C and B connected, and we could have B and C connected and A and B connected. So there were actually 3 possible spanning trees that are a result of this complete graph of 3 vertices. It turns out that from a completed graph, the number of possible spanning trees equals n to the n minus 2, where n equals the number of nodes or vertices, all right? Did it work for this 3-node graph? Well, it turns out 1, 2, 3, right? So we have 3, let's say 3 to the 3 minus 2, that's equal to 3 to the 1, which is equal to 3. Yes, we did have 3 different possible spanning trees. Now, what about this 4-node complete graph? Well, the complete graph has 1, 2, 3, 4, 5, 6 edges, all right? Well, if n is equal to 4, then 4 to the 4 minus 2 is equal to 4 to the 2, which is equal to 16. That means that there are 16 possible spanning trees that are a result of this 4-vertex completed graph. What if we go to 5? Well, for n equal 5, then 5 to the 5 minus 2 is equal to 5 to the 3, which is 125. Well, 125, that's an awful lot, and I'm not going to draw them up here. Why is it important to have this a discussion about a spanning tree? Well, if we have a network, let's just say we have a network of computers, and there's actually a cycle in it, then it is possible if I send a message, let's say I'm sending a message from node A to node B in this drawing. Well, the message may pass to this router, and that router may pass it up to this node, which may pass it down, and you may actually end up with a message that is caught in a cycle. In fact, the protocol for Ethernet has a certain field in it called the time to live, and it's a number where the message, where it originates, there's a value put in it, and every time you make a hop, that value is decremented by 1. You make a hop, it's decremented by 1. You make a hop, it's decremented by 1. If you receive a message and you decrement that time to live from 1 to 0, you just throw the message out because it's assumed it got caught in a cycle. Now, the next definition we're going to talk about is something called a weighted graph. You know, we started out with this idea of alternate ways to represent graphs. And so let's just say that I have these 4 nodes here, A, B, C, D, and I've got connections like that. Now, we showed that we could use a matrix to represent this graph. And whenever it comes to an undirected graph, in other words, each one of those edges doesn't have a direction, well, that means that our matrix is going to be symmetric. If there's a connection from A to B, there's also a connection from B to A. So our graph would look like this. And I actually don't have any loops, so there's going to be zeros on the diagonal. But I have a connection from A to B and from B to A. I have a connection from B to C and from C to B. So B to C and C to B. And then I have a connection from B to D and from D to B. So B to D and D to B. And then I have one from D to C and from C to D. So D to C and from C to D. Notice that this is, in fact, a symmetric graph. Now, what we're saying about weighted graphs, in this case, each one of these edges is considered of equivalent weight, equivalent importance, or, you know, whatever it is that represents that connection, each one of those connections is equal. But it is possible that some resource or some sort of a cost is associated with each one of these connections. So we might have, for example, a weight in the connection of A to B of 5. So for the A to B and for the B to A, those weights actually are no longer 1, they're 5. All right. And maybe the connection from B to C, maybe that's a 3. And so B to C, this suddenly becomes, let's see, C to B and B to C. So we take those guys and replace them with 3 and 3. And maybe C to D and D to C, that's 4. So we make this, what was that, C to D and D to C, that's 4. And then the connection from B to D, maybe that's a 2. So this guy becomes a 2. And this guy becomes a 2. And now what we've got is a weighted matrix that shows the paths and the cost that's associated between each one of these connections. Now, if we want to figure out the best way, perhaps say to get from, I don't know, from A to D, then the cost going A, B, D is 5 plus 2. The cost going A, B, C, D is 5 plus 3 plus 4. Which way would you prefer going? Well, it depends on what that weight represents, right? And so whenever we're looking at these weighted graphs, making a tree out of them, it would behoove us to figure out the best way in order to remove certain edges to create the best possible tree for our application. Now, these weights may represent any number of things. For example, if it's a map between 3 cities, it may be the distances between the 3 cities. If it is perhaps a connection network, it may be the amount of time that it takes to transmit a message between those 2 points. If it's a roadway system, maybe what we're looking at is the number of lanes. So what's the throughput for that particular path. It may be the amount of time it takes, any number of things. So we could be talking about distance, capacity, which would be bandwidth or number of lanes of traffic, the required resources. It could be cost, actual money, or time. So what I'm doing is I've got this 3-node, this ABC, 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 ABC. I've got these 3 nodes, and maybe I've got 8, 5, 2 as the different weights. Well, what I'm looking at is what is the overall weight of each one of these spanning trees. So I've got 8 from A to C, 2 from C to B. I've got 5 from A to B, and then 2 from C to B, and then I've got 8 and 5. So I can add together the weights to come up with a total weight. So this guy would be 10. This one's 5 plus 2, that's 7. This one's 8 plus 5, that's 13. It looks like this tree right there has the minimum weight. And this brings us to the last definition of today's lesson, a minimum spanning tree. Now, a minimum spanning tree is, out of all the options we have for this, this spanning tree, which of these options gives us the lowest overall weight? Now, the problem is that with 3 nodes, this was pretty easy, right? 4, we had 16 possible connections from a completed graph. It may be that we're not starting with a completed graph, but if we are starting with a completed graph, there were 16 possible spanning trees. Which one was the minimum? Well, that's getting a little bit more complicated, but not too bad. But what if we go back to our airline with 5 cities? 5 cities, that's 5 to the third, or 125 different spanning trees. Are you up for evaluating all of them? No. So let's come up with some algorithms to simplify that process. So let's go back to our example of our little airline that wants to fly or connect Chicago, Detroit, let's say, how about Indianapolis, Columbus, and maybe Pittsburgh. Okay, so maybe Pittsburgh is not a Midwestern town, but let's just include it. All right, so Chicago to Detroit. Chicago to Detroit is 240 miles. Chicago to Indianapolis, well, that's 160 miles. Chicago to Columbus, 280. And Chicago to Pittsburgh. Chicago to Pittsburgh, 410. All right. Now, Detroit to Chicago is 240. Detroit to Pittsburgh, that is 205. Detroit to Columbus is 160. Detroit to Indianapolis is 240. All right. Now, let's do Columbus. Columbus to Indianapolis. Columbus to Indianapolis is 150. And Columbus to Pittsburgh is 160. Is that it? We're missing Indianapolis to Pittsburgh. So Indianapolis to Pittsburgh, that's 330. I think we got them all. So what are we going to do in order to figure out a minimum spanning tree? Because what this startup airline wants to do is have the shortest routes in order to connect all 5 of these together. It can't provide a direct route for every one of them, just way out of its league. So we're going to first look at something called Prim's algorithm. Now, Prim's algorithm uses a process of going node to node to node. The goal is to add 1 vertex at a time without creating a cycle until we have a full tree. Now, the first step is to simply pick any node or vertex. So we could, for example, pick Chicago. Now, the idea is next, select the shortest or least weight to connect to a node not yet in the tree. And by doing this, what we're going to do is we're going to add that node or pull that node into our tree and then go ahead and do it again. So continue until we're looking at the cardinality of the number of edges, right? So the set of edges is equal to the cardinality of the number of vertices minus 1, because that's going to give us a tree. And as long as we do not add a cycle, and as long as we don't connect to a node that's already in the tree, we're not going to add a cycle. We should be good until we hit this point when we should have a connected tree, a spanning tree. And this point, we should have a minimum spanning tree. Let's apply Prim's algorithm to our graph up here. Let's start with Chicago. What is the edge that has the least weight from Chicago to a non-connected node? Well, all the other 4 nodes are not yet connected, so any of these 4 could possibly be one of our connecting edges. So we got 160, 280, 240, 410. Looks like 160 going out to Indianapolis is our best bet. So we add the 160, that edge. All right. Now I've got 2 vertices, 2 nodes in my tree. What I'm looking to do is see what the shortest connection coming out of either of these. So we're looking at any of those edges that goes to Detroit, Columbus, or Pittsburgh. So from Chicago, we have the 410, 240, 280. And then from Indianapolis, we have the 150, 330, 240. So it turns out, and don't worry about that 160, it's already been included, and you can't go back to Chicago, right? So 150 to Columbus, that looks like our best bet. So 150 to Columbus. All right. Now, I've got 3 nodes in my tree. I need to now take a look at all the connections from those 3 nodes to the unconnected nodes, Detroit and Pittsburgh, to see which one is the least. So we've got 410, 240. We've got 240, 330, and we've got 160 and 160. So it looks like it's either one of the 160s. Turns out we can pick whichever one we want. Still is going to give us a minimum spanning tree. So let's go ahead and pick the 160 going to Detroit. All right. There you go. So 160. Now I've got 4 nodes, and now let's look at all the remaining edges, the weight of each one of those edges headed to Pittsburgh from each one of the nodes. So we've got 410, 330, 205, 160. So that 160 is going to take us to Pittsburgh. All right. Now, the weight of this tree, the total weight of this tree is 160 plus 160 plus 160 plus 150, which is going to give us what, 630? All right. So 630 is the weight for this particular tree. Turns out that if you come up with any other spanning tree that connects all of these cities, you're going to have a weight of 630 or more. 630 is the absolute minimum. Let's try another algorithm, see if we come up with a similar tree. This algorithm is called Kruskal's algorithm. Now, Kruskal's algorithm, remember, Prim's said we're going to add nodes one at a time until we come up with our tree. Kruskal's is adding edges, and so the goal is to add one edge at a time by adding the smallest edges first until we get a full tree. So, step 1, sort edges from lowest to highest. Okay? And so what you can see is I can actually come up with a table that sorts all of these in order. So for example, we've got Indianapolis to Columbus. That's the shortest. So we know we're going to include that one. And so you're just sorting them from lowest to highest. And then what you do is that if edge, starting with the lowest and going to the highest, if edge doesn't create cycle, add it to our edge group. And once again, continue until the number of vertices is equal to the number of edges plus 1. So let's try this with this graph. Not starting with a node, we're starting with an edge. So if you look at all of those edges, the smallest edge is that 150 between Indianapolis and Columbus. So you add the 150 between Indianapolis and Columbus. And by adding that edge, we've added the 2 endpoints for that edge. Now, we take a look and see what the next largest one is. Well, the next largest one, we've got 3 160s. We could pick any one of them. So we're going to go ahead and pick Chicago. And that gives us a 160. And next one, we've got a 160 going to Detroit. We add that one. And then we've got a 160 going to Pittsburgh. And we have created our minimum spanning tree. And look, we've got 160, 160, 160, 150. We've got exactly, it turns out we have exactly the same spanning tree. It is possible that you may get different spanning trees based on, whenever you had a decision to go to this 160 or this 160 and so forth. The end result, though, should have exactly the same weight regardless of which minimum spanning tree you came up with. All I can say is I'd much rather apply Prim's algorithm or Kruskal's algorithm in order to figure out the minimum spanning tree for this, rather than coming up with the 125 different spanning trees and figuring out which one was the smallest.